Welcome back to Who Wants to Be a Mathematician. I'm your host, Mr. Hill. We're continuing on with AP Calculus Related Rates Part 2. This is where we're going to start the actual word problems. Last time we did some examples of setting up some related rates questions. So last time, just as a review, we had like y squared minus xy equals 2. We had to find dy dt. So we took a derivative with respect to time of the whole thing, and then we knew some information. We knew what x equaled, we knew what y equaled, we know what dx dt equaled, that was like 1 or something, and we just plugged in the information and solved it. So all of these things were given to us. So in these next problems, we're going to have to figure out what each one of those things actually means or is. Alright, so here we go. So step 1. We're going to sketch a picture of the diagram or label it, all that sort of thing. So what the heck is going on with the word problem and what is it asking us to do? Then we're going to write down the known information. We're going to say, what are we trying to find when such and such happens? We're going to formulate general equations, and then we're going to differentiate and then just solve. It's kind of a straightforward thing, but we'll see. So for the first part, let's draw a diagram. So let's read the question. A fire has started on a dry open field, and it spreads in the form of a circle. So suppose we might be doing something with a circle. The radius of the circle, radius, I know what a radius is, increases at a rate of 6 feet per minute. Find the rate in which the fire area is increasing when the radius is 150 feet. So we drew step 1, draw a picture. I mean, we could put in some like fire going on here, get some yellows in there and some reds. We got our fire, and then the really good flames, blue down at the bottom. We could draw a log if we wanted to, get some browns, but let's I guess skip all that. That's distracting. So we drew a diagram. Fire spreads in an open field, form a circle, and the radius is kind of what we're dealing with. So that's step 1. We drew it. So step 2, what is our known information? Well, we know that it increases at a rate of 6 feet per minute, and that's the radius. So the radius increases at a rate, also known as a change, also known as a slope, also known as a derivative. So rate of change, so it's changing, our radius with respect to time is changing at 6 feet per minute. So that's what we know. Do we know anything else? No, not really, because step 3 says find the rate at which the fire area is increasing. So the fire area, the area with respect to find. So find the rate of the area. That's what we want to find when our radius is equal to 150 feet. So that's what we're trying to find. So let's write down a general equation of what we know. What is the equation of what are we trying to do? Oh, we're dealing with a circle. Let's try writing an equation of a circle. What components do we need? We need an area, and we know radius. Do we know anything about a circle when it's talking about area and radius? Well, yeah. We know that area is equal to pi, which is delicious. Just made a pumpkin pie, and it's very yummy. Is equal pi times r squared is equal to our area. So there we go. What are we trying to find? Well, we're trying to find the derivative of a with respect to t. So let's implicit differentiate all of this jazz. So this is going to be step 5. Let's go back to blue. Blue is a lovely color. So we're going to differentiate this whole equation with respect to time. So if we do that, we're going to get derivative of a with respect to time is equal to pi times 2r dr dt. So that's all good and all, but what do we know? We know this and we know that. So the derivative of our area with respect to time is equal to 2 pi times, what's our radius? 150 feet, times our change in rate, which is 6 feet per minute. So if we bring that all together, the change in area with respect to time is equal to 300 times 6, that's 1,800 pi feet per minute. That's kind of crazy. Think about that. Pi is like 3 point something. So 18 times 3, that's 30. 8 times 3 is 24. So that's 5,400 feet. This is about per minute. That fire is traveling so fast. And if we divide that by 60, we could get it per second. That's so 60. Well, I mean, you could do the math, but that's crazy to me. That's crazy. That's really fast. But we have found our answer. Our solution: at what rate is the fire's area increasing when the radius is 150 feet? So when our radius is 150 feet, that means we are now increasing, our area is increasing at a rate of 5,400 feet per minute. That's crazy. That's crazy. But we're not here to talk about crazy. We're here to talk about math. So let's continue on with the world. So suppose a cone-shaped icicle. Ooh, winter's coming up. Yay. So icicle. Ooh, we're still on blue. Let's draw our icicle. Icicle. Could draw little driplets coming off the bottom. Little driplets. So a cone-shaped icicle is melting, and the radius is decreasing at a constant rate of that. If h is equal to 10r, how fast is the volume changing when the radius is 10 inches? Well, let's draw our diagram. We got our diagram. So that's a bad radius. We're just gonna go with that. That's our radius there. So known information. Well, what do we know? We know the radius is decreasing at a constant rate. So our r is decreasing. So the change in rate of our r is decreasing. So it's negative because we're decreasing inches per minute. And what does it ask? It's asking us to find how fast was the volume changing. So dv dt when the radius is 10 inches. So r is 10. So general equation, oh look, we have a nice cone. So general equation of a cone, I like switching colors, so let's switch colors at this point. General equation of our cone is going to be the volume, because we're looking for this, is equal to, anybody? 1/3 pi r squared h. But they threw us a little tiny curveball. The h is going to be 10 times the radius at this point. So we're just going to rewrite this. We have 1/3 pi r squared times 10r. So that's going to be our equation. So now we have to differentiate with respect to time, WRT, with respect to. So we're taking the derivative with respect to time of our v is equal to 1/3 pi, or I guess it's 10/3 pi r cubed. All I did was simplify that right there. Change it around, you'll figure it out. So we take the derivative, we get dv dt, excuse me, is equal to 10 pi thirds times 3r squared times dr dt. So we change this around, we got 10 pi r squared times dr dt. What do we know? We know our dr dt is negative something something something. So negative 10 pi. And what else do we know? We know our radius is 10, so 10 squared times negative 0.1. Ooh, 0.1 inches per minute. So we change this around. This cancels out with a 10, because 1/10 and a 10 cancel out. So we have 100 negative 100 pi inches per minute. And what is that? That is our change of volume with respect to time. So there you go. Pretty straightforward stuff. And it's not a whole lot of craziness going on. So we're going to finish the rest of the packet in class, and we're going to start on some more problems. So hopefully this gave you a good explanation and grasp of where we're at. And here we go.